Hello, my name is Larry Lapides. I'm with Imperas Software, and I'll be talking today about virtual platform-based development environments for low-power mixed-level safety-critical systems. My colleagues on this are Duncan Graham, also from Imperas, and Soren Schreiner and Kim Grutner from Office in Germany. This work was partially funded by the SafePower project under the EU Horizon 2020 program. There's a website for more on the SafePower project, and we'd like to thank all the organizations that participated in SafePower, both the universities and the commercial companies. The agenda for today is to talk first about safety and security in embedded systems, then to talk about the SafePower reference architecture that we used, the virtual platform environment, the SafePower platform using a Xilinx Zyng 7000 FPGA, the virtual platform challenges and solutions, and then the results and a summary. The story here is that embedded systems in multiple industries, for example, aerospace, automotive, railway, have multiple levels of safety and security requirements. These are mixed-level criticality systems. The goal for the SafePower project was to build a reference architecture for managing the complexity of these systems. Virtual platforms are an approach to increase the development efficiency and productivity for these systems. And so what this project did, or at least this task of this SafePower project, was to compare the hardware and virtual platform-based methodologies to validate the advantages of the virtual platform approach. So let's start with safety and security in embedded systems. What we're seeing, what everyone is seeing, is that the industry is demanding faster and more efficient systems. Faster, of course, means more processors. The initial architectures to satisfy these requirements just consolidated smaller SoCs and the processors on those SoCs into a larger SoC with minimal sharing of resources. This satisfies the performance and domain isolation requirements, domain isolation for safety and security critical use cases. Note that with these smaller SoCs, we likely had different levels of criticality, therefore the mixed criticality systems. For these SoC consolidation architectures, power consumption becomes a real issue in terms of both reliability and cooling costs. So the question becomes how to achieve more efficient systems while still satisfying the performance and domain isolation requirements. One approach is larger, faster processors. In other words, processor consolidation with a hypervisor providing the domain isolation. On now to the SafePower architecture. SafePower reference architecture incorporated larger, faster processor with both hypervisor and physical tiles to meet the performance, efficiency, and domain isolation requirements for mixed criticality systems. We see here with this hypervisor-based tile, this is actually running on the dual-core ARM Cortex-A9 processors, and we see in particular a power monitoring application in the hypervisor, as well as additional user applications. And then there are these additional bare metal tiles, which are eventually going to be implemented in the FPGA fabric in the programmable logic. And these provide additional spatial isolation in addition to the hypervisor-based isolation here. On top of this, we have a time-triggered network that is controlling the system. So let's look at this in more detail. We're using a tile-based architecture connected via a time-triggered network on chip. These tiles are managed by a type 1 hypervisor. So this type 1 hypervisor allows for an arbitrary number of user partitions. We're showing 3 different partitions here, including the power monitoring application, but there could be any number of partitions. And in fact, later in this presentation, we'll show 4 additional partitions here. The bare metal tiles are not directly managed by the hypervisor, but they are connected to the time-triggered network on chip. And they implement a light version of the hypervisor interface so that the hypervisor can communicate with these bare metal tiles. And then the time-triggered behavior is executed based on a pre-computed communications schedule that triggers the message injection times. This achieves both the spatial isolation and the temporal independence that's required in safety standards such as IEC 61508. This time-triggered architecture also provides deterministic scheduling of software tasks, with worst-case execution time analysis supporting the achievement of timing requirements for those safety-critical systems that have hard timing requirements. On to the virtual platform now. For the virtual platform, we use the Imperas tools. There are 3 key areas here that we want to focus on. First are the virtual platform models themselves. This includes the CPU models, both ARM and microblaze, the peripheral memory components, and then the overall platform itself. These models are built with APIs, with the APIs supported by the simulator engine. This is a just-in-time or binary translation simulator engine that translates ARM or microblaze instructions into x86 instructions for execution on the PC host workstation. And then the third piece of this are the tools, the software verification, analysis, and profiling tools, including things like tracing, profiling, code coverage, memory monitoring, OS-aware tools, and also things like fault injection, which we'll get into a bit later. And then there's a native debugger in this environment. Certainly the environment can be used with GDB or other third-party debuggers, but in this case we use the native debugger as it supports the heterogeneous platform that we're using, and also supports peripheral driver code debug, so a hardware software code debug capability. The virtual platform used existing models from the Open Virtual Platforms library if those models were available. So this included models of the ARM and microblaze processors and various non-processor models. There were also new models built using the OVP APIs as required. These included the network interface, various peripheral components, and a hierarchical parameterized platform so that we could build actually different platforms with different partitions depending upon the application that we were using the SafePower platform for. These models are provided as open source. They're available on the ovpworld.org website. The simulator product is the Imperas MStar SDK product. This is an instruction-accurate simulator, runs very fast, 250 million instructions per second, performance for the fully loaded platform with the multiple microblazes and the dual-core ARM Cortex-A9. This also included the MPD, multiprocessor debugger for platform-centric debug, and those software verification, analysis, and profiling tools. So on to the details of the SafePower platform implementation. The objective here was to build the platform as both real hardware and a virtual platform. So we chose the Xilinx Zinc 7000 board. This has a processing system, which is a static hardware block, which includes the ARM Cortex-A9 dual-core processor. There is also a programmable logic block, the FPGA fabric, where we can define any components and interconnects, including the microblaze processors, network-on-chip nodes and interconnect, and also the memory. And of course, as this is a Xilinx FPGA, we can create and dynamically load any programmable logic definition. Regarding interconnect, there's a fixed connectivity between the processor system and the programmable logic. This uses address map data and GPIO. And we also have the power control and monitor built in with power monitoring devices to enable us to set voltages and obtain feedback for the current values, and also the clock control so that we can dynamically change the processor clock frequency. So together, this provides us with a dynamic voltage and frequency scaling system, or DVFS system. In addition to the hardware implementation, the hypervisor is critical to the SafePower platform. We use the Extratum hypervisor from Fentis. We see here, as we dive deeper into the block diagram of the SafePower architecture, we have the Extratum hypervisor running on the dual-core ARM processor. It's got the power monitoring application here, and then shown here, 2 different partitions. Plus we have, in this case, 3 microblaze-based tiles in the programmable logic, and these are all connected by the time-triggered network. So the Extratum hypervisor supports the time-triggered task management that's required in this architecture, and supports special partitions for system-level applications, such as the power monitoring and management. So how do we change the hardware implementation into the virtual platform implementation? One of the key things here is to understand that we do not need to build the complete hardware implementation in the virtual platform. We only need to build in the functionality for the software that we are testing. So in the processing system, we have the dual-core ARM Cortex-A9. We have things like the Ethernet MAC. We have flash controller. We have UART to provide a console. We have a memory controller, but actually we only built as much of the memory controller as we needed to build. We have memory out in the fabric in the FPGA. And then we also have the smart loader to help us do a quick boot. And we have this visualization interface, which helps us to provide effectively a GUI onto different elements of the virtual platform, where you might have flashing lights in the real hardware. We're providing a visualization interface. And then this programmable logic is where the individual tiles are implemented. So just looking at that programmable logic in a little bit more detail, this is connected to the processing system by the network on chip. This uses a packet-based structure, and you can see we've got the network interface here, as well as GPIO interfacing between the processing system and the programmable logic. And here we're showing 3 different tiles in the programmable logic, each with microblaze, each with local memory, and actually there's additional logic in each of these as needed. So on to the virtual platform challenges and solutions. There were 3 challenges that we faced with the virtual platform. The first was how to model the DVFS. Second was the fault injection testing environment. And the third was supporting the time-triggered system. Regarding the DVFS, the key thing was to be able to calculate an estimated power consumption dynamically as we're executing different applications here. So what we were able to do is, in the same way that we used Slipstreamer to implement the different software tools, we've got effectively a custom tool with this Intercept library that implements the power model. This power model understands the processor core, it understands the rest of the platform. It has formulas in here effectively understanding the power consumed per instruction that's executed. It also understands clock rates and various other parameters. And it provides a file output. This file output then gets fed back into the voltage regulators and power sensors, coming through the I2C bus and coming back into the processor that way. So the power sensor is represented by this I2C interface, and the power model then gets new voltage values and returns power values to the voltage regulators and the power sensors. So this means that next to the frequency configuration, the application is able to configure the voltages and to request the current power values. Here what we're showing is executing Linux in the virtual platform with the attached power model. We've got the Linux console here. We can see that we've booted Linux, but actually here in the simulator output, what we're doing is reconfiguring the frequency of the processors. In this case, each processor is going to be running at 333 megahertz. We can see this here. This is a derating factor of 50%. And also the DDR frequency is set to 533 megahertz. So again, also derated. And this is just as it would in the hardware, this is going to slow down the processors and reduce the power consumption for this particular example. For fault injection, we've got a fault injection framework that will include different faults and different fault campaigns, and apply the simulation time to trigger the injection of faults. So again, we're using something similar to that binary intercept library, and we're able to use that to implement faults in memory, in the memory monitoring, in the GPIO, in the partition scheduler, in the hypervisor, to reset the different CPUs and also the interrupts. And we can see here that we've used that visualization interface that I pointed out before to build a GUI, a user interface that lets us control the different faults, including the simulation time where things are going to be executing. So we can just click these on and off to determine the fault campaign to be run here. The third challenge was to be able to support the time-triggered scheduling. In a virtual platform, in any virtual platform, not just with Imperas, the default simulation scheduler runs a quantum, a set number of instructions, and runs them first on one processor and then on the second processor core, and if there are more, runs on the third processor and so on, and then goes back to the initial processor. And this is a set number of instructions. So this can be functionally correct, but has limited ability to understand the timing. So in the SafePower system, with this time-triggered system, the timing synchronization was defined statically, essentially before boot. And these time triggers are not necessarily going to align with the simulation quanta. So what we did was to develop a time-triggered scheduler where the applications are executed until we reach the next event. So each quantum is scheduled to complete the work, and we detect the points in the application for the synchronization events, as we show here. Last, let's talk about the results. So with this platform, with both the hardware platform and the virtual platform, we implemented railway and avionics use cases. We evaluated the functionality and timing with and without the low power techniques on both the virtual platform and the hardware platform. The objectives were to demonstrate that the software components interacted correctly with each other and with the hardware, to verify that the entire system complies with the requirements, both the functional and the extra functional requirements, including the low power requirements of each use case, and to show that the power savings can be achieved for safety critical applications in different domains. Here I'm showing a block diagram of the avionics use case. The hypervisor has partitions for the power monitoring app, for the maintenance recording system for this flight system. There's a flight control system, video image processing system. There's also an internet connection. These are not the safety critical systems here. They're running with the power monitoring app on the ARM processors with the hypervisor, the Stratum hypervisor, controlling this. The safety critical systems are actually physically isolated in the FPGA fabric. These are these three microblaze systems for the actuators, the flight control system, and the flight control system with the LDU. And these are, again, all connected with the time-triggered network. So for both the avionics system and the railway system, or those use cases, there are two key results. First, the virtual platform test results were equivalent to the hardware-based results. So tests could be run on both platforms. That means the functional tests, the extra functional tests running DVFS, the fault injection tests, these could all be run on both platforms. The virtual platform uses the same binaries as are run on the hardware, and so the virtual platform can be utilized in the test and certification of safety critical applications. The second key result is that the virtual platform provided benefits over the hardware platform for development, debug, analysis, and verification of the software applications. The first of these benefits is in execution control. Simulation is deterministic as compared to the non-deterministic hardware execution. The second is a unified debug environment. With the virtual platform and the Imperas tools, including MPD, there is capability for simultaneous debug of all application code executing on all processors in the platform, including providing access to peripherals. When a breakpoint is set on one processor, all processors stop when that breakpoint is reached. In addition, analysis tools such as profiling, code coverage, dynamic assertions are implemented non-intrusively, so there is no modification or instrumentation of the source code required. Second, we were able to implement the power interface library using that Slipstreamer API, which enables support for real-time power management techniques such as DVFS within the virtual platform environment. The third key area was fault injection, flexibility, and control. The virtual platform provides visibility and observability, so faults can be injected anywhere in the platform, in memory, in the processor registers, in the GPIO. You've got much more flexibility and control than with the hardware. With the hardware, you can only inject faults at the ports, and here you can inject anywhere. The fault injection is implemented by an external library, so the fault generation can be controlled. You can have purely random fault generation, or you can have a controlled and pre-specified distribution of faults that are injected for your tests. So in summary, the virtual platform was used for development of a mixed criticality system. There were several challenges that were encountered and overcome: power modeling for power monitoring and management, fault injection testing, and support of the time-triggered system. The virtual platform environment had equivalent results to the hardware platform, with a number of advantages due to the controllability, observability, determinism, and the ease of automation of the software simulation. Thank you very much.